Hello friends, welcome to VK lectures. In this lecture we are going to discuss about Gauss law and its application. So now here we are going to learn about the Gauss law. Okay. So it is related to the electric flux. Electric flux. Now what do you mean by the electric flux? So flux is a number of field lines uh, or lines of force. Both are same, the field lines and lines of force. So number of field lines or lines of force passing through a unit area. So if the number of field lines are more, the electric flux is higher. And since it's a number of field lines in a unit area, the flux is a scalar quantity. So the flux is a scalar quantity, and that's given by the small. Now if we consider this as the area, or there is some flux, then if you consider this as the electric field is in this direction, and the area vector, this is small area ds, and its area vector is along this, that can be written as n cap. That is the area vector pointing towards the perpendicularly outward. Then the small flux d phi is given by the electric field dot ds, or ds en cap. This also can be written as e dot ds, and that is e ds cos theta, and theta would be the angle between this area vector and the electric field. So this is where you can write theta. So theta is the angle between the area vector and the electric field. Now the total flux phi can be written as the integral over this surface. So you can write the integral over this surface, e dot or eds cos theta. Now there are two cases here, when the electric field is uniform and when the electric field is not uniform. Non-uniform electric field and uniform electric field. Now for uniform electric field means constant electric field. Uniform electric field the uniform electric field E is constant, then the phi can be written as the E can be taken out because it is constant, integral ds or ds cos theta, and this angle theta will not change, so that will become E cos theta into integral ds. So that's equal to, so here the cos theta can also be taken out, so this becomes E cos theta integral ds. integral ds is nothing but the total area, so that's equal to E a cos theta, so that's equal to vector E dot a, so that's 5. Now when there is this is case 1, and for case 2 you don't have to simplify anything. The total flux phi will be equal to integral over the surface E ds cos theta. Now let's see here that when the we have the formula, the flux phi is equal to E dot A. Now that's equal to EA cos theta. Now let's consider a surface, something like this, and the electric field is in this direction, and area vector is also in the same direction, so that's ds or area vector. Now the electric flux phi is considered to be positive because these are both in the same direction, so that's electric flux phi is positive, and when they are in opposite direction, so, or let's take another case in between where the electric field is along this direction perpendicularly upward and ds here, so this gives the flux phi to be equal to 0. Okay, now another case can be the same area. The ds is, that means the area vector is towards the right, and the electric field along this direction. Now the flux phi is considered to be negative when electric field and the area vector is in the different direction. Now let's also find one example here. You have a charged particle q kept outside a closed surface, say for example this is a closed surface, and through the surface the electric field enters. So when the electric field enters, the electric field is in this direction and the area vector is in the opposite direction. Okay, and this electric flux, when it comes to this the opposite surface, is in this direction. Electric field direction won't change, but the surface is outward. Both are in the same direction. So here if I say this is phi 1, and here we have the flux phi 2, phi 1 is negative because electric field and the area vector are in the different direction, and phi 2 can be considered positive because they are on the same direction. Now this is the reason why when you have a closed surface and a charge is placed outside this, then the total flux becomes 0. Now here, based on the previous concept, we are going to do a problem. Now here, consider a closed cylinder kept in a uniform electric field So let's the uniform electric field be E. Find the total flux through the cylinder. Now here the electric field is moving in this direction, so this is what we have to assume here. Now we need to find the area and the total flux. Now based on the surface we can identify there are uh, three different fluxes from phi 1, which is from this first area, and now here we have the curved surface. This is the curved surface, and through this we have phi 2, the flux phi 2, uh, and this is another area, flat surface, circular surface, and through this we have phi 3. Now there are three surfaces, that is 1, 2 and 3, and the total flux, since it's a scalar quantity, the total flux will be sum of phi 1, phi 2 and phi 3. Now let's see what is phi 1. So phi 1 is equal to E dot A1, E dot A1, so that's electric field is uniform dot A1. Now we need area of this. Now let's say for example this has got the radius equal to, so let's say this is the radius capital R, and this length, let this length be equal to uh, uh, L. So phi 1 equal to E dot A1, so E dot A1 area is pi R, capital R square, into, and the angle between, now this is important, angle between this can be written as E A1 cos theta 1. No, so this is angle is, this is electric field is in this direction, as we know, towards the right, and the area vector will be pointing outward, so that will become 80 degree. So that's equal to cos theta 1, so theta 1 is 180, so that's equal to minus E pi capital R squared. Similarly, let's take for phi 2, which is the curved surface area. So phi 2 will be equal to now E dot A2 into cos theta 2. Now E dot A2 dot A2 into cos the angle. Now E is in this direction and the area vector is along, this is A2 direction, and electric field is in this direction, so this 90 degree, cos 90, this becomes 0. Now comes to phi 3, E dot A3 equal to E A3 cos theta 3. So theta 3 area vector is along this direction, same as that of the electric field, so angle between them is 0. So E into A3, that is pi R square. Now total phi is equal to phi 1 plus phi 2 plus phi 3, that's equal to E times pi capital R square with a minus sign here. So minus plus this through the second surface, that is the curved surface, is 0 plus E into pi R square capital R square. So the total flux through the cylinder when placed in an electric field, external electric field, the flux is 0. Find the flux through curved surface area. So here we have a pot. This is the surface area that we see, and over this you have this curved surface area. Now the question is to find the flux through the curved surface area when the electric field is E is given and it is in this direction towards the right side, and the mouth of the pot has the radius equal to capital R, and the electric field is in this direction. Now through the curved surface area and through the flat surface area, we can write the total flux phi is equal to phi 1 plus phi 2. So let this be phi 1, and through the curved surface area let that be phi 2. Now since electric field is outside, starting from outside, and there is no charge inside the uh, pot, you can write this is total flux equal to 0, that is phi 1 plus phi 2. Now phi 2 is the curved surface and phi 1 is the flat surface. So let's find out phi 1. Phi 1 is equal to E dot A or E dot A1. So that is equal to E dot A is pi capital R squared into, now that is the area vector will be perpendicular outwards, so pi times R square, that is cos theta, then theta will be equal to 180, so that is equal to minus E pi R squared. Now what is phi 2? Phi 2 is equal to, from this equation, phi 2 equal to minus phi 1, because the total flux is 0. So phi 2 equal to minus phi 1, and phi 1 we already have got minus E into pi square, that's equal to minus of minus E pi capital R square, that's equal to E pi capital R squared. So this is the flux through the curved surface area. Gauss law in closed surface. Here we have to know that this implies we are enclosing a charge. Enclosing a charge. So this is what is we mean when we say that it is in a closed surface, because so far we were dealing with some surface being placed in an electric field, but now the electric field is produced within the closed surface. So here we have a charge q which is producing the electric field, and this is placed inside the surface or inside a closed surface. Now according to the equation, we have d phi equal to E bar dot ds bar, and that's equal to EDS cos theta, and this implies that the total flux phi equal to integral E bar dot ds bar. So that's the total flux. You can write closed surface to indicate the complete sphere. So here we have, this is a sphere of radius capital R enclosing a charge small q. Now d phi is equal to E dot ds, and the total flux phi can be written as integral d phi, which is equal to integral E bar dot ds bar. And what is the electric field? Now we need the electric field at this particular point or the surface. So electric field at surface E is equal to 1 by 4 pi epsilon naught, assuming that it is free space, and q is the charge, and capital R square, that is the uh, mm, radius of the sphere. So that is the electric field. Now ds is in the direction of r only, so that we can write r cap. So the electric field will also be in the direction of r cap. Now we know this total flux phi equal to integral 1 by 4 pi epsilon naught q by r square, or like this capital R square, into ds. So before that we have r cap dot ds into r cap, because ds is in the direction of r cap. So now can take whatever constant quantities are there, 1 by 4 pi epsilon naught capital Q by, sorry, small q by capital R square. R dot r cap is 1, so integral ds. So closed integral ds, that is the total surface area of the sphere, that will be 4 pi capital R square. So that's equal to 1 by 4 pi epsilon naught q by r square into 4 pi capital R squared. So 4 pi r square and square get cancelled. So total flux phi is equal to q by epsilon naught. So this is the flux in surface which is enclosing a charge q, and we have to note that it is independent of the surface of dimension of the surface, dimension or shape of the surface. That means the flux phi, when it is inside, that means the electric field is produced by the charge inside the surface, then the total flux is independent of the dimension or the shape of the surface. Arbitrary surface enclosing a charge q. Now what we are going to do is we are going to prove the Gauss law for this arbitrary surface. Earlier we have done it for a sphere. Now we are going to do this Gauss law, or prove this Gauss law for arbitrary surface. Now assume that this is a three-dimensional figure with at this point let us have the charge q, and this is the surface over which we are going to calculate the uh, the total flux. So this is the electric field, and the same will be the area vector ds. Now from this point, if you can draw, so this will look like a three-dimensional figure. So this can be, instead of theta, we can write it as a d omega. It looks like a cone. uh, so here, so this angle is nothing but d omega in a three-dimensional figure instead of a triangle. So uh, d omega, which is the solid angle which is represented as d omega, can be written as d omega is equal to ds cos theta by r squared, ds cos theta by r square. Now if theta is equal to 0, d omega is equal to ds uh, by r squared, and from this we can write ds equal to d omega r squared. Now here uh, we can calculate the total surface. Integrate s is equal to ds, that's equal to integral d omega r squared. Now let's say we are going to calculate it for a sphere. For sphere, we know that the total surface should be equal to 4 pi r squared. So the integral ds should give us 4 pi r square, that is integral d omega r square should be equal to 4 pi r square for the sphere. Similarly, for an arbitrary surface, the total surface should be equal to the total surface area of that sphere, or for that arbitrary surface. So this is how we can calculate the total surface area for any arbitrary surface. Now, as we have seen, let's consider here as our small surface where we are going to calculate the uh, phi flex or d phi. So this is the ds, and almost in the same direction we have the electric field. Now des vector can be written in the form of ds n cap, where n cap is the direction of the electric field or the surface. Now the electric field at a point r distance, so this be r distance from q, so electric field will be equal to k q by r square in the direction of r cap or en cap. So now what is d omega? D omega is nothing but ds cos theta by r squared, or ds can be written as ds equal to d omega times r square divided by cos theta. Now for an arbitrary surface, for arbitrary surface we have the d phi given by uh, electric field dot the ds en cap. Okay, now that's equal to electric field is k q by r square. Instead of n cap, let's write r cap for time being, and dot ds n cap, and that's equal to kq by r square ds into r cap dot n cap, that's the uh, angle cos theta. So let's write r cap dot n cap itself. Now mm, instead of des, we can substitute ds from here, and that's equal to kq by r square. ds is equal to d omega r square divided by cos theta, and r cap dot n cap is nothing but cos theta, because r cap is a unit vector. R cap dot n cap equal to magnitude of r cap into magnitude of n cap into cos of angle between them, theta. So r cap and n cap are unit vectors, so r cap dot n cap equal to cos theta. So this is equal to d phi, so we can remove out all the uh, uh, factors. R square and r square get cancelled, cos theta and cos theta gets cancelled. So now we can write d phi equal to kq into d omega. Okay. D omega, or you can write phi is equal to integral kq d omega. Now that's equal to uh, k and q are constant, so that is 1 divided by 4 pi epsilon q into d omega, that is the total solid angle in any solid material is equal to 4 pi. So integral d omega, so that's equal to uh, q divided by 4 pi epsilon times 4 pi, that's equal to 4 pi gets cancelled, q by epsilon. So this is the total flux, that is q by epsilon naught. Gauss law and application. So here are few figures or the surface given, and the brown color what is given here is the charge q placed uh, near to the surface. So we need to find out the flux passing through that given surface. Now according to Gauss law, we know that the flux is equal to q by epsilon. Now this here we have a sphere and hollow sphere, and inside we have the charge q, then the total flux through the surface will be equal to q by epsilon. Now coming to the second case, the charge is placed just outside the hemisphere, and this is the surface that we have, that is the plane surface, and here we have the curved surface. Now the total flux passing through this curved surface will be equal to that. To understand that, we have to consider another hemisphere, which by which we can complete the total sphere. So now in this situation, the phi is equal to q by epsilon naught. Since we have two hemispheres, the question is about the first half, so you have to multiply by 1 by 2, so that's equal to 1 by 2. That means the flux is passing through one out of the two surface. So we have two surface here, the flux is passing through one out of two surface, that is again once again you can write like this, q by epsilon naught into the flux is passing through 1 out of the total of the two surface that we have, so it is q by 2 epsilon naught. Now similarly here in the case of cylinder, we have to assume that there is another surface here. So the question is about what is the flux through this part. One is the curved part here and another is the plane surface. So here also, if you consider it as closed, this is one part, this is another part, it should be same distance. This distance has to be same from here to here. Okay, so total flux will be equal to q by epsilon times 1 out of the two parts that we have seen. There are two parts to this, from here and upward and below, so 1 by 2. So again phi is equal to q by 2 epsilon naught. Here are few more examples. So here we have to consider one more cone towards the down part. So the total flux will be equal to q by epsilon times 1 out of the two part. Now here is a different case. Here the charge is placed on one of the sides, and here again you have to construct another square. So now we have constructed another square so that it completely encloses this charge. So now again phi will be equal to q by epsilon times 1 by 2, because we have constructed another square. Now here a slightly different case from the previous ones. We have a square which is enclosing a charge q which is inside the square, but we are asked to find out the flux through the shaded region, in the yellow region here. And now we can consider that the total flux phi is equal to q by epsilon naught. This is total, and similar to this shaded region, we have another shaded region here. We can construct how many number of shaded region we can have. So here we have 1 2 3 4 5 6 7 8 9 10, and on the other side 11 12. So there are 6 faces. Each face will have has 2 shaded region. So likewise there will be 12 shaded region. So the phi, actual phi, that means the flux through the shaded region will be equal to q by epsilon times 1 by 12, 1 out of the 12 faces that we have, or the 12 region we have, that's equal to q by 12 epsilon. Here we have a similar question. Here we have a square. Assume this is a square, and we need to find the flux through this surface due to this point charge q. Now since we have one face of the square, we have to construct a cube out of this square. So we are going to construct the cube, and to construct the cube we need 6 more faces. So now we have constructed the cube, and we know that the total flux through the entire cube is equal to q by epsilon naught, but we don't have the surface of the cube, but we have only one single side, that is the square. So one out of the 6 faces, we need 6 faces to construct the cube, and the total flux will be equal to q by epsilon naught into 1 by 6. So we have to check first that how many such squares are required to construct required to enclose the charge. So to enclose the charge we need another 6 more faces or squares. So that's why the total phi equal to q by epsilon naught times 1 by 6. Here is another question. The question is, we have a cube given, and on one corner of the cube we have placed a charge q, and we need to find the total flux moving through this surface. Now which surface is this? No any specific area, the entire surface, through the entire surface of this cube. What is the flux? Now we need to construct, using this cube we need to construct another bigger cube such that the charge q is being enclosed perfectly. To that we need to construct cubes on the left, on the upper left, and on the left part. So this is right, this is upper right on the upper left, and here we already have. And similarly we need another 4 more. Here we have 4, another 4 more we have to construct. To understand this, here is a yellow color region is the given figure, and this is where the charge is being kept. So this is the charge q, and to enclose this charge q we need to construct, here you have another cube, 1 2 3 4 5 6 and 7, 7 plus 1 8. So total number of 8 cubes are required. So total flux will be equal to 1 by 8 times q by epsilon naught. Now what is the question you need to ask here? How many cubes are required to enclose the charge? The answer is 8 cubes. So total phi will be equal to 1 by 8 times q by epsilon naught.